how to balance chemical reactions. In order to do this, you want to be really comfortable with going from the name of an ionic compound or the name of a covalent compound to the formula of that compound, because that will be often the way that the question is phrased. Chemical reactions will always take the format of reactants on the left-hand side and products on the right-hand side. And there'll be this reaction arrow in the middle that tells you a chemical change is happening. Because really, chemical reactions are just another way of saying chemical changes. There are some rules for chemical reactions that we want to be aware of. The first one is that the same types of elements occur on both sides of the reaction. So if I have a reaction that has one blue element and one red element, and they make a molecule, and they are reacting with one black element, those are my reactants. Then I have my reaction arrow. And my products, let's say, are my black element has now formed a compound with my red element, and my blue element is now by itself. Notice a purple element does not randomly jump into the reactant side. So everything that I started with, every type of element that I started with, shows up both in the reactants and in the products. They're not necessarily in the same combinations. This is the basic idea behind a chemical change, is that you're breaking and making bonds. You're rearranging things, or else it wouldn't be a chemical change. The second rule to keep in mind with chemical reactions is that you have to have equal amounts of each type of element in the reactants and the products. So let's say, for example, I started with a molecule that had one black element and was attached to two blue elements, and that this reacted with two red elements in a molecule. On my product side, it turns out that my red and my blue get together and form a molecule, and my black gets bumped out. Now, notice here that the way I've written this is on the reactant side, I started with two blue and two red. But on the product side, I only have one blue and one red, because I haven't actually balanced the reaction. The process that we'll take in doing this is we will adjust what's called the coefficient, which is the number out in front of the molecule, to make sure that I have equal amounts of each type of element in both the reactants and the products. So at this point, I know that I've got two blue things in the reactants and two red things in the reactants, but only one blue and one red in the products. So what I will do is put a 2 out front here. At that point, now I'm letting my whoever the reader is, I'm letting them know that really what I have is, on my products, I'm going to rewrite this up here. Whoop. On my product side, I have a blue and a red attached as a molecule, and I have another blue and a red attached as a molecule. That's what the 2 blue, red, whoops, keeping all these inks in order can be troublesome. That's what that tells me. 2, bloop, right there. Okay. Now, sometimes it's tempting to, rather than change the coefficient out front, to change the subscripts in the chemical formula. That's a big no-no. Don't do that. We don't do that. You can change the coefficients out front. You cannot change the subscripts. The other thing you can't do is use fractions as coefficients. So I couldn't have said that I had, say, 1/3 of this. Or actually, this would be more relevant if I erase this and erase this. I can't have said that I had 1/2 of a red molecule. That's not okay. We don't use fractions. So no fractions as coefficients. The other thing to keep in mind, do some more erasing here, is that when I'm all finished here, I should have the lowest whole number ratio of coefficients. So lowest whole number ratios. So let's say I had balanced this. Oh, my molecule here is having some troubles. Let's say I had balanced this and I came up with there were 2 of these and 2 of these and 4 of these and 2 of those. Each of those values, each of those coefficients can be divided by 2. So they are not the lowest whole number ratios. So I would take an additional step, cross those out, make this a 1, and this a 1, and this a 2, and this a 1. Okay, let's do an example. I've written here the reaction that happens when your airbag in your car steering wheel goes off. When the steering wheel, when the airbag inflates, they want it to be needs to be a really fast reaction, and it needs to put a lot of gas into the airbag really quickly so that you don't bonk your head, among other things. And so they use sodium nitride. Excuse me, this is not sodium nitride. This is, I'm totally losing it. Sodium, I'm not even going to guess. We're just going to leave it for now. I'll look it up later. So I've got NaN3 on one side of the reaction in my reactants. Here are my reactants. And on the product side, I have some sodium and some nitrogen. And my job here is to identify whether I have equal amounts of sodiums and nitrogens in the reactants and the products. And if I don't, I need to adjust the coefficients so that I do. So what I'm going to do is write my elements right down the center here. And then I'm going to look and see how many of each I have. I see I have 1 sodium on the reactant side and 1 sodium on the product side. I see I have 3 nitrogens on the reactant side, and I have 2 nitrogens on the product side. So I don't have a balanced reaction because I don't have equal amounts of nitrogen on both sides of the reaction. To adjust that, to fix that, I need to adjust my coefficients in front of each of my substances. Now I'm noticing I've got an odd number here and an even number here. And generally, a way to cope with that kind of problem is to turn your odd number into an even number by multiplying by 2. So that changes my 3 to a 6. And it also impacts the sodium, because that 2 applies to the entire molecule. So this becomes a 2. Now I can look at my products. Well, now I have 2 sodiums, so I'm going to put a 2 there. That's looking pretty balanced. And now if I put a 3 in front of the N2, I will have 6 nitrogens. And I double check to make sure that I have the lowest whole number ratio. Yep, can't divide anything out. I don't have any fractions. It's looking good. This reaction is balanced. Now, one thing I want to note before I go on is you might have noticed that this element, nitrogen, was listed as a diatomic molecule. There are certain elements, and they're called the Silly 7, which you'll see why here in a minute, that when they show up by themselves in a balanced chemical reaction, they show up as diatomic molecules. And they are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. 1, 2, 3, 4, 5, 6, 7. So part of why they're called the Silly 7 is because there are 7 of them. And the other reason is that you look at the periodic table and you find nitrogen, it is element number 7. And if you go from nitrogen, oxygen, fluorine, chlorine, bromine, iodine on the periodic table, guess what? It makes a 7. Whew, good way to remember that. Now, in that reaction that we just looked at, you produced sodium in the reaction that was making the nitrogen that was inflating the automobile airbag. Problem with sodium is that when it gets into contact with air, it ignites. It bursts into flame. So you really don't want that running around in your airbag. So there's an additional reaction that happens in the airbag. The sodium will react with some iron 3 oxide to produce sodium oxide and iron. Iron's okay to have running around, that's just metal filings pretty much. And our flammable sodium has been converted to sodium oxide. Now notice in this example, I didn't write out the formulas for you. I gave you the names of the substances, and you have to translate them from the name to the formula. Let's go ahead and do that. We've got sodium, not one of the diatomics, so it's just written as sodium. iron 3 oxide, which is Fe2O3. Those are my reactants. The reason I know that is because it tells me this reacts with this, and then it says to produce these guys. So here are my products, and here are my reactants. Okay, let's see, sodium oxide, Na2O, and iron. I'm going to list my elements down the middle here to help me keep track of how many of each I have. And we see on my reactant side I have 1 sodium, on my product side I have 2, on my reactant side I have 2 irons, on my product side I have 1, and on my reactant side I have 3 oxygens but only 1 on the product side. When faced with a reaction like this, which has 3 different elements, and sometimes you'll have 4 or 5, it's a good idea to leave the elements that are by themselves as balanced last. There isn't always a really clear place to start in balancing chemical reactions. Sometimes you have to just kind of jump in and mess around with it for a little while and cross things out, and eventually you'll arrive at the right answer. I know this will drive some of you nuts, because you like to start the problem and arrive at the solution very smoothly. It's very clean. Balancing chemical reactions, though, it can get messy. And let's take a look at this. I'm going to randomly choose to start with iron. Well, no, iron's all by itself. I'm going to start with oxygen because it shows up in the compound in both places. And I see that I have 3 oxygens on one side but only 1 on the other, and so I'm going to make that a 3. That changes my oxygens to 3 and changes my sodiums to 6. Now I just have elements left, so this actually comes pretty easy. I changed that coefficient to a 6, and I changed my iron by putting a 2 in front of it to a 2, and now everybody's balanced. This reaction looks at the decomposition of sodium bicarbonate, which is baking soda. And it's a really interesting reaction because you produce carbon dioxide, and that's what causes your baked goods to rise. So we have NaHCO3. It's decomposing, so there aren't any other reactants, into sodium carbonate, carbon dioxide, and water. I'm going to list my elements down the middle, and I see 1 sodium and 1 hydrogen and 1 carbon and 3 oxygens. And in the product side I see 2 sodiums and 2 hydrogens and 1 carbon, and I have a lot of oxygens. I've got oxygens here and here and here. So I'm going to add all of those up, and I see that I have 6 oxygens. Another way sometimes to approach problems like this is to notice that you have a polyatomic ion here, and to look and see if you have the polyatomic ion somewhere else in the problem. When that happens, you can actually balance polyatomic ions. So I could have written CO3 -2 and balanced carbonates. In this case, I'm choosing not to because I have carbons and oxygens in so many other different places. But that is a shortcut that works really well when you have polyatomic ions on both sides of the chemical reaction. Okay, so we've got quite a lot going on here. I'm going to start with the sodiums and just see if that takes care of my problem. I'm going to put a 2 here, and that changes this to a 2, and then it impacts everybody else in there. It changes this to a 2, and this to a 2, and it changes this to a 6. Alright, so my sodiums are looking pretty good, my hydrogens are looking pretty good. I made a mistake on my carbons. Did you catch that? Hey look, I had carbons in 2 places. I had a carbon here, and I had a carbon here, which means in my products I had 2 carbons, not 1. Which means those are